Let's see.
I think we can start. Our next speaker is Lukas, and he will tell us about exploring heterotic models with reinforcement learning and genetic algorithms. Please.
Okay. Well, thanks very much. Thanks very much to the organizers. Thanks very much for the opportunity to speak. So yeah, I'll be talking about applying reinforcement learning and genetic algorithms to certain string models. And this is joint work with Steve Abel, Andre Konstantin, my student Thomas Harvey, and it can be found in these papers down here. So here's a quick outline. So after a very brief introduction, a general introduction, and then a brief introduction into reinforcement learning, I'll be talking about a toy example briefly, which I think is a nice illustration of reinforcement learning. And then I'll be applying two certain string models, monad string models in the heterotic context, first RL and then genetic algorithms, and see how they do on these types of models. And then I'll conclude, of course. So, well, string theory and machine learning is not such an old topic. It's about 4 years old, and there's been quite a lot of work being done over the last 4 years. But I think it's fair to say that a lot of it has been in the context of supervised machine learning, and so a lot of different types of data that appear in string theory has been analyzed in that way. And in fact, we've just seen an example of that in the last talk. And of course, these kinds of analysis that can lead to very interesting directions and conclusions, as we've also just seen. But of course, if we want to deal with the nature of the string landscape, the very large number of string vacuum, then supervised learning is probably not going to help us all too much. But we need some kind of effective search algorithms. And reinforcement learning in the context of machine learning is known to be very effective on large environments, as very impressively shown by this AlphaGo 0 project. And by now we also have indications from string theory that this is a fruitful direction in the context of various types of string models, intersecting brain models, line bundle models, and flux vacua and monads, which is what I'm going to talk about. So this seems like an interesting direction to pursue. Now, genetic algorithms, they have a long history starting in the 60s. And I've given this sort of a nice reference here if you're interested. And they're, of course, also known to lead to very efficient searches of large environments. But they haven't been used terribly much in our field. In particular, there have been a few applications, I think, to my knowledge, starting with the paper by Abel and Ritzes, who've been applying this to free fermionic models. So the question that I really want to ask here is, can reinforcement learning and/or genetic algorithms be used for string model building? And more specifically, can we use them to construct models with certain desired prescribed properties, such as being close to the standard model? Can we use these to discover model building strategies? Can we use them for a comprehensive search? Can we get all models at least within a given set? And then finally, how do those two methods compare in the context of these tasks? And of course, well, I've just indicated, these things can be studied for quite a number of different classes of string models. We opted for one where, first of all, we don't quite actually know what the outcome is so much. So this is not a very well studied set from the point of view of a comprehensive model overview, this set of monad bundles in the context of heterotic Calabi-Yau models. And it's also a set where the path from the string data to the phenomenological data is a fairly complicated one, so that bottom-up methods they wouldn't get you very far with these kinds of models. Okay, so let me talk a little bit about reinforcement learning. So here's my standard slide for that. So reinforcement learning is not using any precompiled data, but it's getting data from an environment which has in it a bunch of states, here these objects, and an agent is going along, exploring this environment, going from state to state. And as it does, the agent picks up rewards or penalties, depending on whether the state becomes better or worse according to certain goals, and might get a particular reward if it finds a very, very nice state, which is called a terminal state. In this case, in our case, of course, terminal states will be the desirable states, such as states which represent, which are close to the standard model. And this exploration of the environment is not done sort of randomly. It is done in a way that is guided by a neural network, in the simplest case, by a policy network, which takes as an input the state and as an output suggests an action. So suggests which next state the agent should be going to. And these two main components of the system, they interact in the sense that an episode is performed in which you acquire a data set which contains of these triplets of state, action, and reward, and they're then being used to train the neural network according to maximizing the reward. And then this improved neural network is then in turn being used for the next episode, and this process is then iterated and hopefully converges. So how would you apply this whole thing to string model building? Well, the formal mathematical environment for reinforcement learning is called Markov decision process. So this is about matching the ingredients of a Markov decision process to our physical situation. So an environment would be a family of string or quantum field theory models. The states would be specific models. Actions going from state to state would be some small modifications of models that I'll specify. And the reward would be some measure for how far a given state is away from the desired properties. And we've looked at this for two examples. One is, in fact, in the context of quantum field theory, or if you want, beyond the standard model building. So this is not something I'll talk about here, of course, but I'll just point you to this paper if you're interested. So this is in the context of building mass models within the standard model using the Froggatt-Nielsen idea, and you can show that reinforcement learning works very well on that. So here I'll be focusing on the second one, which is heterotic Calabi-Yau models, monad bundles. And well, we'll have various realizations of there are various flavors of reinforcement learning. We have two realizations, one a very basic reinforce, the other one is an actor critic, and they're realized in Mathematica. Okay, so here's a toy example, which I think is nice because it shows kind of how the whole thing works, which is in the context of an environment that consists of line bundles on a given Calabi-Yau. So the line bundles can just be labeled by integers or integer vectors in terms of these integer vectors like so. These are the intersection numbers and the second Chern class of the underlying Calabi-Yau. And we could ask, can we train a neural network so it finds line bundles with a given target index that we arbitrarily assume? So the more specific mapping of the Markov decision process to the environment would be then as follows. The environment would consist of these integer vectors describing the line bundles. An action would be changing one entry of such a vector by plus or minus 1. And there would be a value which measures how far the index of a given state is away from the target index. And the reward would be computed on the basis of this value, or rather based on how this value changes as you go from state to state. And so we can do this for a simple example, the bicubic. We've seen the bicubic before in a very different context. The line bundles on that space are described by two integers, so a very simple example. And there's a very successful training there. So here for example, you see the fraction of terminal episodes. So episodes which end in a line bundle with the correct index, which goes to 100% after well, a very short time. And so we have 100% of terminal episodes. They get there in about 6 steps. And so to see how this works, this is a 2D environment. So that's one reason to look at it. It can be easily plotted. This is the environment. So this is K1, this is K2, the 2 integers. The dots correspond to all the line bundles, and the fat dots correspond to the line bundles with the right target index. And here are 2 examples of the kind of episodes that the trained network will generate, starting from the ping point, which is a random starting point, and then guiding more or less efficiently to a nearby terminal state. And you can do this a little more systematically and find the basins of attraction of these various terminal states. So the terminal states in this plot are just these empty dots here, and the various colored regions are the basins of attraction of these terminal states. So everything in the green region, for example, here, will be guided by an episode that starts in the green region to this empty dot here at the corner. And so what this shows is kind of why RL can be quite efficient at searching. It converts something that would normally scale, like the total number of states. If you performed a scan, you would have to scan over the total number of states, into something that scans more like the number of desirable states, like the number of terminal states. All you need is 1 episode per basin of attraction to find all these terminal states. Of course, that's a rough statement, right? This statement kind of depends on all of these basins of attractions roughly being the same size. If of course, if they are very small basins of attraction, and you already see that this can happen over here, then of course you might need a few more episodes to actually find the terminal states with these very small basins of attraction. But that's a good gives you a good intuition of why RL can be so efficient in searching. And of course, it also shows that geometrical engineering of this kind can be done in this fashion. So now let me get to the main example, which is monads. So monads are a bit more complicated, but we'll also base them on line bundles. So there's an exact sequence which defines our bundle V, which involves 2 line bundle sums B and C. Each is sum of line bundles, so each given by a bunch of integer vectors. And so the number of states here is given by this, assuming that each integer roughly takes 10 values. So H is the H1 on Hodge number of the Claviao, and rank B and rank C are the ranks of those 2 line bundle sums. So this is potentially very large space. And if you look at particular, even small examples for Picard numbers 2 and 3, you see that these are very sizable spaces. Certainly the second one would be too large to search systematically. And more importantly, it's quite difficult to sort of to reverse engineer the right B and C, given that the actual properties of the model are encoded in this bundle V. And what this means is that currently, or before this work, there were very few models, actually very few successful models known that were constructed in this way. Okay, so here's the same match between Markov and decision process for this kind of environment. The environment now consists of these pairs of matrices which represent the 2 line bundle sums. An action consists of, again, changing specific entries by ±1 now in a correlated way. That's basically to preserve the first Chern class condition that we need to preserve. And then the reward is based on this value, which measures the deviation from desired properties, which in this case we take to be close to the standard model. So which in this context means basically the right spectrum and the consistent string model. Okay, so we'll take the bicubic as a first pass, pretty large environment, 10 to the 12 states. And this is something that you can do on a simple computer in about an hour. And so here's the terminal fraction, and you see it has this amazing phase transition where after a certain training time, about an hour, it goes to 100%. And so we'll have a trained network that finds terminal states with 100% efficiency. It gets there in not too many steps, about 16 steps. And if you do a single run like this, then you already find during this training period, you already find quite a number of terminal states. So a few times 10 terminal states during such a run. Now we've tried to be a bit more ambitious than that. We've then tried to use this trained network for a systematic search. So we generated many random initial starting points and episodes from these starting points and checked in each case which terminal states they would lead us to. And in this way, we got to this curve. So this is plotting the number of inequivalent perfect states or terminal states against the visited states, and the fact that this curve saturates kind of indicates that at some point we have more or less found all the states to be found in this environment. So the number is about 600, and they all satisfy the criteria for being a standard model candidate. There are a few more checks to be done, which we are not doing during this training, but let me not get into that. These would be quite difficult to find with just regular systematic scans. And the one model that is actually known within this set, which is a model found some time ago, that is among those 600 that are being found, but there are all these others. So the message here is that this method can indeed be used to find all models within an environment which you would normally think is much too large to do that sort of thing. So we've pushed this a little further to this Calabi-Yau with Picard number 3. So that's even larger. Again, training is very successful. So you get 100% efficiency on these episodes. The length also quite efficient, 22. And we can find large numbers of terminal states. We haven't attempted in this case to do a complete job and find all the terminal states simply because there are too many of them. So this is already at a stage where I think we would have to impose more conditions on what we mean by a terminal state, what we consider a good model, and reduce the number of terminal states. Okay, so this is the RL part, but basically what we're getting here is new databases of standard-like models, which would be very hard to find with conventional methods. So this plot kind of gives you gives you an idea in which order these properties are being satisfied as you go along the episode. So this horizontal axis here is the number of steps in the episode. So that you can take this as some sort of indication of what kind of model building strategy the neural network suggests. Okay, so let me get to genetic algorithms. So that's clearly another efficient way of looking at large environments, but we also actually wanted to have an independent confirmation of whether the suggested completeness of our RL search really holds up when we use a completely different method to search. So to have a good comparison between the two methods, we were actually using exactly the same environment. So the monad environment realized in exactly the same way, except that for the purpose of the genetic algorithm, we take our states, which are represented by this pair of matrices, and we just encode them in a binary string by basically just converting every integer into binary and joining them all together. So each state is a binary string now. And then we assign a fitness to each such string, which is in fact exactly the same as the value function that we've used for reinforcement learning. So there's another I mean, it's another choice that makes comparison of the two methods a bit more meaningful. So then, as you do in genetic algorithms, so maybe I don't have to go too much into the details. Gary gave a nice introduction to it yesterday. So you create a population, in our case, typically something like 250 individuals, and then you evolve this population by a sequence of crossing and mutation. The crossing is controlled by the fitness of the individuals. Here we use a ranking selection for those who know the finer details. And we've tried various styles of crossing, but a single cut crossing, for us at least, does the job. And we mutate with a pretty small mutation rate, typically 0.5% or something.
You have 5 minutes.
Sure, thanks. And the goal of this is, of course, that after a certain number of generations, we'll have a population which has many fit individuals, so many terminal states, in other words. And so here are some examples for results of individual runs. So this is an example on the bicubic. This plot just shows the, it's sort of a histogram of the fitness of the various individuals as a function of the generation, which goes along here. So this is 200 generations. And you know, these large peaks back here, they're telling you that after this number of generations, it really starts to cluster around individuals with very high fitness. And the same is shown here in this plot. So this is the fraction of perfect or terminal states as a function of the generation. So we get to populations which by the end of it are sort of 60% terminal states. And so this is, in some sense, this is very impressive. I mean, I hadn't worked with genetic algorithms before, but this is something, one such run is basically just a few minutes on a laptop. And after this time, you already have the first states. You find your first standard models. I mean, this is in some sense, on this small scale, much more efficient than RL, where you might need a few hours of training time before you can do anything. So this is really incredibly efficient. And for this other manifold with Picard number 3, we can get to similar results also after a very short time. You will find the first models. Now we've done the same as we've done for RL. So we've just performed repeated GA evolutions to really exhaust all the number of terminal states. And so again, this is the curve of states found against visited states. And saturation suggests all terminal states have been found. And perhaps more importantly, if we actually compare the states that we found with those that the RL system has found, there's a very, very large overlap. I mean, it's of course not absolutely perfect, but basically 90% overlap between the two sets. The other remark is that GA in the end is somewhat more efficient. So we need a little less time to perform a complete search. And of course, as I've emphasized, if you want to find a few states quickly, then it is quite a bit more efficient than RL. So let me conclude. So reinforcement learning can be used to engineer topological properties, and it can learn the rules for geometrical string model building. And if you look carefully at the trained networks, it can suggest strategies for model building. At least at small Picard number, we can use RL for comprehensive searches of very large environments. And in fact, genetic algorithms can be used for the same purpose. And at least for our realizations, they turned out to be somewhat more efficient at it. But these two methods, they end up in the end after sufficiently long running times with the same set of models. So this very strongly suggests that we really have performed a more or less complete search here. And many new standard-like models can be found in this way. Now, there are obvious extensions, some of which I've listed here. The real question that we're asking is, can this be pushed to higher Picard number, more moduli? How does it scale when we do so? And is this something that we can perhaps in the end use for a complete scan of the string landscape? So of course, we don't have the answer to that, but that would be, of course, fantastic. So that's it. Thanks very much.
Thank you, Andre, for the nice talk. We have a question from Lara.
Hi, thank you very much.
Hi.
So you didn't comment on stability of these guys, which I understand is a higher level question than the pain, but actually my question was sort of motivated. These techniques seem very efficient at probing complicated structure. Have you guys thought at all about anything you could do to sort of filter or scan for criteria for stability?
Yeah, yes, we did. In fact, there are some necessary checks already in there. In the sense, so of course, stability requires, as you know too well, cohomology calculations, and they cannot be done algorithmically while you run any of these algorithms. That would just be way too slow. But since we have analytic formula for cohomology now, at least in some cases, we can use those to perform some necessary checks. So, of course, there might be some scope there to get to more sophisticated formulae, and so you could envisage in the end perhaps that you can implement this in a sufficiently fast ways. You can actually have a complete stability check carried out during training or GA evolution. We haven't quite done this yet, but at least there are necessary things in there.
Gotcha. Just to throw one other comment out there, I mean, back in the day when Bert and Volker and I were working on the connections numerically, we found that the Donaldson algorithm could actually be used as a probe of stability quite rapidly in that case, and that you could actually tell if things weren't converging very quickly. So I haven't thought about this properly, but just to throw it out there, I mean, with the improvement in metric algorithms, including your package, maybe that would be something that would be viable at a later date, as well as to actually filter by beginning a connection computation, and you can see very quickly it goes wrong.
Well, I'm not sure about that. I mean, that you're proposing sort of two very large computations at the same time. So for every state in
that at the same time,
the
that would be
process that you visit, you would have to then run another neural network training that would perform such a test as you suggest. So that would be
more as like you find your data set and then later you try and filter. But yeah, I don't know how viable it would be.
Yeah. Okay.
Yeah. Thank you.
Okay, thank you. More questions for Andre? Okay, I want to ask something. In these models, in these new models, are there some particular signatures from the phenomenological point of view that are different from the models that we already know? Let's say the vector-like exotics, or what other features? So how close can we get to something more phenomenological in that sense, beyond the standard model?
Yeah, I mean, we haven't really started looking at the details of the model. I mean, phenomenological details. What we have done in some cases is to take some of the checks in there, they're only necessary checks, right? So such as stability, as just mentioned. So if we get this set of say 600, in principle, the next step would be to check stability and see how many survive that. So typically there's a few hundred which survive that. And then another check which isn't carried out during training is the existence of mirror families, because that would also require cohomology, which is at present too slow. So that would be another check. So we've done this in some cases. And again, there's quite a number there which survive that test. And then presence of a Higgs pair is another test. So we've done this at least for a subset, and there are definitely models which survive these things. So in the end, there'll be models there which have the precise standard model spectrum and are consistent string models. That we can say for sure.
Harry has a question.
Hi, Andre. Nice talk. Yesterday we had this discussion about which algorithm is better in solving the problems. I was trying to advocate that it's not really the computational speed, but rather what you can learn from each of these algorithms. For instance, in this case, you could compare, what kind of models are being sampled from genetic algorithm or reinforcement learning, and you could do a simple PCA or any other classification methods on the bundles that you sample in your search.
Yeah,
have you looked into this?
We have looked at the details of that. I mean, you can sort of look at the rollout in the GA case as well. I'm not sure you learn all too much from that. What we can say is, I mean, I haven't really touched on this. There's sort of a fairly large degeneracy in our models, which has to do with being able to permute the line bundles, so that doesn't really change anything in the actual string model, but they're formally different states. And the GA is very good at sort of sampling this degeneracy, which I think has to do with the basic crossover mechanism basically being consistent with this permutation degeneracy. So that's something that the GA does fairly efficiently. So we get models, many degenerate models many times being served by the GA.
So for instance, I would expect GA would take you from one basin of attraction to another, whereas reinforcement learning doesn't. So this kind of comparison would be much more meaningful.
Yeah.
Comparing efficiency is like comparing apples with oranges in this case.
Yeah, well, I don't know. I mean, our goal here, I'm not sure it's apples and oranges, right? If the goal is to, it depends what you want, right? Our goal was to do a complete search and, think what you want about it, but the GA is fast at doing it. Okay, that's the statement.
Okay. Let's thank Andre again.
Thanks.
And